to the COMCA. Our speaker today, our guest, Professor Lauri Viitasaari. I would like, on behalf of the organizing committee, thanks for coming to Chile. With your wife, our little guest, Ellie? Ellie. The conference is Stochastic heat equation considered quantitative approximation results. It's from Helsinki University.
Yes. Okay. Thank you. So first I would like to thank Marco Corcini for the invitation. And also, well, Ingrid Torres. This is my third time in Chile. Every single time I have loved it here. And first time in Barcelona. But so, basically, well, 3 of you knows me quite well already, but to the rest of you I would like to start maybe by introducing myself. So, my name is Lauri Viitasaari from Finland, very far away. As you can see, I have quite a world explorer.
Beautiful country. I was there.
You have been there?
Yeah.
Thank you.
You're welcome.
I don't care whether it was a lie, still thank you. Okay, well, basically my interest in alphabetical order, so not ordered by any other means, is, well, some things related to statistics and probability. Ice hockey only on TV, so I'm not on national team, as you can maybe see from my outfit. And then, as every Finnish person, I love sauna. Or okay, if you're from Finland, you love sauna, or you lie and you say you love sauna. But on the maybe on research related, so I always try to get new collaborators. I work on statistics and probability quite a lot. So this is some kind of list. But of course I have only 1 hour today, so we have to drop something. Let's put the lottery machine on. Let's drop all of this in red. So today we are left, I will speak about stochastic partial differential equations, which are related to or driven by Gaussian processes. And then I will try to, as I mentioned in the title, some quantitative approximation results, so it's related to also to limit theorems and statistical inference. And so this is a joint work, based on a joint work with Yingui, David Nualard, and Panku Chen. So I pronounced all the names correctly. Okay. So this is my outline. So I have like 1 hour. I have 3 topics: introduction, my actual results, and then I will speak a little bit about the proofs. And well, I have 1 hour to market my work, so section 2, but I will spend like 3 minutes to that. So I will spend most of the time by trying to motivate you why these questions are interesting. And then for the proofs, I will not focus on the proofs of our results, but I try to explain you the methodology we are using, which is a very powerful tool in general to obtain like limiting distributions or quantitative approximation results. So whatever problem you're interested in, I try to explain you what you can do in the general case, and then as a byproduct we just apply to our case and get everything. Okay, so let's start with the introduction. What is stochastic heat equation or stochastic partial differential equations? So as we all know, I don't know your backgrounds, but all of us know that partial differential equations usually describe many phenomena in real life. And as an example, okay, I have a heart there, you could have any other constant, but heat equation, here this is just a Laplacian. It describes the distribution of heat in some body over time. So, something to write on. So, I will study a ball here, or, well, I will explain what kind of bodies you can consider. But you consider a ball, and then you have some heat there, so it's warmer here in La Serena, and very cold in Helsinki, here. But within time, the heat should distribute if there is no external forces, equally to the whole ball. But basically, in principle, okay, this is the simple case. But what happens is that it might be that you have some external force affecting it. Maybe you don't know what this external force is, so you can model it with some random thing. You don't understand it perfectly, or it is random. It can be really an external force, or maybe caused by some measurement errors. You don't know exactly how your equipment works, like this mouse here. You don't know what is inside that. And then what you get as a result is a stochastic version of your partial differential equation. And I will speak today mostly about the stochastic version of the heat equation, but I will explain a little bit what other stochastic PDEs you can consider. Okay, so what is the stochastic heat equation? It's exactly our heat equation, deterministic one. Here, this is Laplacian, but we add some random thing. So here, sigma is just some Lipschitz continuous function, and then you have the solution u. So it depends kind of your random external force. The magnitude depends on your solution, so where you are. And then you have some, I mark it as v dot. It's just your random thing there. In our case, we consider, or in many of the cases in the literature, it is assumed that you have here some Gaussian noise, so generated by some Gaussian field, and then you have some covariance structure. And here I will look at the covariance, which is white in time. This simply means that if you look at the time increments, what happens to your external Gaussian force, you look at the time increments, they are independent. So the increment from today to tomorrow is independent from the increment from tomorrow to the day after, and so on. But then it has some memory in space variable. So this is just the standard Euclidean metric, and it's given by the Ritz kernel there. And I will give also analogous results in the space-time white noise case. So here D is dimension, and basically the beta has to be less than dimension to ensure integrability, but this is technical stuff. I try to skip all that. And you could consider, of course, that you have white both in time and in space. I will soon come to the part where I try to explain why it is very complicated. So, for example, if you have white in both space and time, even the solution exists as some random process only in one space dimension. And it is not understood even in two space dimensions what happens with the equation. I will explain soon why this is so complicated in comparison with the deterministic case. And this is kind of, well, why we wanted to put some covariance in space to get well, let's say three space dimensions. This we would like to have, yes? To use our example of La Serena and Helsinki and Luego as our body. Okay. So, and also, okay, I have the constant initial condition, but it's straightforward to extend. This is kind of for simplicity to some classes of initial conditions. So is this simple? No. It's very complicated, and of course I have to admit this is purely a very subjective opinion, because this is something I can barely understand, so I want to believe that this is very complicated. If you disagree, don't tell me. But let me at least try to convince you, kind of giving you a little bit of Finnish attitude and convince you that life is very hard after all. So why this is hard? Basically, the point is that if you look at this, sorry, wrong direction, here, if this is smooth enough, then this is, you could understand this in some classical ways. But interesting random forces are not smooth, they are not differentiable. So, for example, in this, if you consider that maybe you have independent time increments, so this is kind of corresponds to the y in time case, then you get only Hölder continuity. So you don't have differentiability. In our case, it really has the independent increments in time, but has some correlation in space, but doesn't play much of a role. Still, we only get Hölder continuity. And okay, so you cannot speak about the derivatives or absolute continuity with respect to the Lebesgue measure. But if you consider these interesting cases, they are not even of bounded variation. So you cannot understand them as a measure. You cannot use standard Sobolev techniques because you don't have even weak derivatives. Usually you only have bounded p variation for some p, which depends on the Hölder continuity. And so you have non-differentiability. So even in the first place, we cannot understand this as a differential equation anymore. It is understood as an integral equation. So you integrate both sides. This is kind of for stochastic differential equation, for example, in the classical case, this we understand simply as this. So this is the integral equation, and we are studying this equation. The same happens here, but still, okay, you understand it as an integral equation, but what kind of integral? And well, the original thing, which is kind of the stochastic differential equations, not partial, driven by white noise, so by Brownian motion. Then you can use the Ito integral. This dates back to Ito, to 40. And then kind of generalizations to Gaussian processes. You can use so-called big Ito integrals, which is based on a white noise analysis. And okay, here I'm just basically, a lot of people are working on all of these topics, but I'm just giving some names who have made major contributions, plus I'm mentioning me. But anyway, then okay, Christian Bender and we did some generalization of the big Ito, that's one possibility. Divergence integrals, a lot of work done by David Noalard. Works for Gaussian processes and Gaussian fields. So everything here is kind of a Gaussian thing. Then you can consider pathwise integrals, which is kind of means that you look at omega by omega, you forget all the randomness. and there is a lot of different concepts. By Fölmer, Seele, I have done some work on this direction, where you have Hölder integrators of sufficient order. And then there is the rough paths initiated by Terry Lyons, and a lot of work developments done by Martin Heider. And the last is the regularity structures, which led to the Fields Medal to Martin Heider in 2014. So there's a lot of different concepts of integration, and none of these are very simple actually. And why this divergence is in blue is that this is how we understand our integrals here. Of course, for example, in the Brownian motion case, all of these are the same. You can understand that they are produce the same thing. But in general, this is not the case. And for example, these divergence integrals or big eta integrals cannot or is not extended beyond Gaussianity. Okay, so I hope you are on the same page with me now, and I think also this is maybe not so easy. Let's go back to the equation. So what we get is a unique solution like this. And now, okay, this is again understood as an integral. So this is a divergence integral or Ito-Mauss integral. It doesn't matter. Just you can think that we can define some kind of integral with respect to this noise here. And this is what is understood there. And then you have the initial condition here. And what are these objects? So you have the sigma, that was the given function. And then you have P, which is just the d-dimensional heat kernel. And that's the fundamental solution to the deterministic case. So if you drop the random part, your heat kernel is just your solution. It's kind of well known, and maybe some basic course in analysis you prove this. But this is the solution, and this is my random object I'm trying to study. I try to understand what kind of, let's say, a probability that it satisfies whatever, it belongs to some set of whatever I'm interested in. And it depends now on the space variable and time variable. What is known is stationary in space. This is, if you know something about these stochastic integrals, it's not hard to prove using the isometry. If you do not know anything, then just trust me. And then it's also bounded in LP uniformly over all compacts inside. And this is what we know, but that's not much yet. And why this is the solution, so I can basically try to convince you. So this is the solution, and why kind of at the same time you see what you would try to, what you're supposed to expect as a solution. So here, let us differentiate. I want to rewrite the equation again. This is my equation. So let's look at this one here and differentiate in time. And let's do this formally. So you differentiate in time. You have t here and t here. So first term is you just differentiate inside the integral. Let's assume we can do that. And then the rest term is that you integrate this one, which is kind of that you simply plug in t in place of s. This is kind of, in the classical calculus, this is how the chain rule works. And then you have kind of this term, and it's in this one because it does not make sense in this form. But then what you get is that we know that the heat kernel here is the solution without this. So the time derivative of that is simply the Laplacian and half here. So this part here is actually also, if you differentiate or look at the Laplacian with respect to space, so this is exactly this one here. And then from this part, which is on this, so you have P0, that's the Dirac measure. So you integrate with respect to y. Only thing what you get is point at x. And this is kind of formally how you can do it. And then if you consider this b dot as the differential of this b, then this is what you kind of, it's natural thing to expect. But of course you have to make this precise by understanding everything as an integral like this. Okay, we have the solution, and we know it's stationary. It's bounded in LP, so expectation and all the higher moments exist. But what else we know? It's very complicated. If you look at this one, so even this integral is very complicated. And here you have additional function, and you're integrating the solution applied with this function itself. So it's very hard to kind of understand the statistical properties of this object. And what you basically, okay, what is known, if we just wait, then this solution stabilizes to something understandable. You get some limiting this, okay, you get something random in the limit, but it stabilizes to something stationary. If you consider what happens in the deterministic case, then it's simply, if there are no forces, there's no sun, eventually all the heat from La Serena will spread to Helsinki and everywhere, and it's just the same temperature everywhere. We just wait enough. So same happens here. Problem is that if we don't have time to wait, I want the heat wave to Helsinki now. And this is okay, of course here it's winter, in Helsinki it's summer, but it's still warmer here. I don't have time to wait. So what can we do? We want to a fixed time t tomorrow, let's say, and we try to understand something about the distribution. But okay, what can I do is that, on the other hand, are we really interested on the temperature of one particular point, or maybe on an average over hopefully large body? So let's say I'm not interested on the exact temperature of this point here, but rather the average temperature in the whole hall. And if our hall is large enough, let's hope that we can do something. And let's put these questions into the form of mathematics. So I take some large body or some body, A, and we look at the average. So integral in space for fixed time t tomorrow. And we try to analyze the properties of this. And basically I have three questions I'm trying to answer here. First one is that, okay, for given moment t in time, if A is large enough, can I approximate this distribution somehow? So the U, the solution itself, is very complicated, but when I take the average in space, it's still very complicated, but hopefully it is close in some sense to something that I can understand. And then I can basically give some, well, do some exact computations. Like let's say it's the limit is normal, then every one of us can draw probabilities from a normal distribution with basically with our phones, not my phone, but maybe yours. Okay, if this is the case, then also we want to study the approximation error. So maybe it's close. How close? This is in mathematics always okay. You can say that it is roughly something, but usually in practice you're interested what this roughly something means, how close you are. And then the last thing is that, okay, these first two questions are on a particular moment in time. But if we look at this, not letting t to go to infinity, but look at it as a random process that evolves in time. Can we approximate that as a stochastic process? So some random object which evolves in time. And for each of these questions, I try to give you a short motivation. So first, can we approximate this? It's very complicated. Consider the classical central limit theorem. It says that, okay, this with large n, even if you have independent random variables, it's very complicated to write the distribution of this down exactly. But standard normal is very easy to understand, and we have this by the classical central limit theorem. So this is kind of what we are trying to do here as well. Also, although our object is a little bit more complicated. Okay, how large is the error? This is very important question also, and I will give you a simple example, which you can find from some unnamed statistical textbooks still. So let's take independent Bernoulli random variables, and then you want to find a confidence interval. You do not know the parameter p. You try to find a confidence interval of some level, and it's given like this, and then you can even sometimes see, okay, good thing is that this is kind of the conservative way, and it does not depend on the true value of the parameter p, so you don't have to know that. And if you have, let's say, 100 observations, then you can apply central limit theorem. It's kind of a large enough amount of observations so that central limit theorem applies. You are close enough to the normal line. Just do your computations. And if you look at it a little bit closer, so the probability is approximately that the true parameter belongs to here is, let's say, okay, 1 minus alpha. Let's say you are looking at the 90% confidence interval. So that means that the probability is approximately 0.9. If the true parameter happens to be very large, even with 1,000 observations, you get 0.3 error. You can imagine, you consider that, okay, you are working at the company, you say to your boss that, okay, the probability is 0.9, close enough, approximately. The true one is 0.6. You end up losing billion of dollars or Chilean pesos. I don't want to be around when your boss finds this out. So we also kind of want to really see that even if you have something in the limit, how far you are. And then the third one, can we study this or approximate this as a stochastic process, so something that evolves in time? Again, let's consider the classical central limit theorem. This is approximately normal. But what you have even more. You don't look at the n observations, but okay, this should be floor function here. But let's say t is 1/2. you look at only the n divided by 2 first observations, and so on. And you look at this as a random process. It actually converges to the Brownian motion. And you have a stronger mode of convergence. So Brownian motion, it's normal, but because it converges as a process, what you can say then, you can study the properties of this is your object you're interested in. You can say something more about that by using the properties of the Brownian motion. So for example, self-similarity, so some scaling thing. You don't have to know exactly what the self-similarity means. Independence of increments. This is, for example, what we will get in our case. Of course, okay, here the observations are independent already, so you get the independence of the increments by definition. But if they are not, then this is also might be of interest property. So whether asymptotically, say in our case, that we have this large body, average temperature there, and whether the increment in time from this day until tomorrow, and from tomorrow to the next day, are asymptotically independent. This, of course, this is something very useful we can have. Okay, so I hope you are motivated, why these questions are interesting, why this equation is interesting. If not, I don't know what to do. Take a nap, for example, then for the rest of the half an hour. If you are motivated, then let's go to the second part, which is kind of, I present the results. And I promised I'd spend 3 minutes to this part. Let's extend that to 5, but still. So, what we are studying is kind of that, okay, I mentioned that we want to study also the approximation error. So how far we are from the limiting object. And what we use is the total variation distance. It's defined like this, and it defines a metric for probability distributions. So, okay, f and z are random variables here, but you just, what you take, you look at the probability that this some event A happens, so this random variable belongs to A, where A is some Borel set, and you take supremum over all possible Borel sets. So what is the interpretation? You look at the maximum difference between the probabilities of some events, kind of the worst case scenario what can happen. And then maybe in practice you are interested like huge losses if you're working at the company in this example. If you can count this total variation distance, then that particular probability you are interested in is always less than this, because this is kind of the worst over all possible events, what is the maximum difference between probabilities. As a particular case, people use Kolmogorov distance, or if you're familiar with the Berriesen bound on the classical central limit theorem, it gives you the maximum distance between distribution functions. This is kind of even stronger thing. And here's the result. So it looks technical, don't worry about that, I will explain it a little bit. What we have is that our object, okay, I'm looking at the ball, this example. So large ball, centered at origin, and then we let the radius of the ball grow. So this capital R is very large. This is my large body here. Okay, this is easy to extend, I will explain soon how. But let's, for simplicity, consider a ball. And then what we look at is that we were interested to approximate the distribution of this one. So, as in the classical central limit theorem case, this -1 is simply that you remove the expectation. And then we divide with the standard deviation to get variance 1. Oh, sorry. And then we compare this to the standard normal variable in the total variation distance. And what we get is that there exists constant that depends on our time point t. In our example, t was 1, so tomorrow. And then it depends on the beta, which was the given parameter of the covariance kernel, the Ritz kernel. And this is, we can explicitly really compute it, the constant c. And then you have this capital R here to power something. So you can explicitly compute the constant c here. So this bound gives exactly how large your capital R should be so that the maximum error is, let's say, 1%, so less than 0.01. And of course, as a byproduct, we get convergence towards standard normal, because this is kind of even stronger than only convergence, weak convergence towards normal. We get even in this distance, strong distance. And okay, this is, we divide with the standard deviation so that this whole object here has variance 1. Of course, in practice, you might consider only like, in the classical central limit theorem, you sometimes, okay. Sometimes you see this, and sometimes without this. So this is kind of only the asymptotic of the variance for this, or the standard deviation. So the same here. This is kind of the asymptotic standard deviation. So you could replace the sigma r with this one, and still get the limited normal. Okay, some remarks. Of course, if you're familiar with the central limit theorems, and in particular central limit theorems for stationary processes, we can use actually central limit theorem for stationary. Remember that this solution was stationary in space, and we are integrating in the space variable. So you get that. We can prove also that this covariance decays quite rapidly. So then we can get the limiting normality by some very classical central limit theorems for stationary processes. Of course, now we get the error rate also. And then, okay, this was the assumption here. Sorry. Okay, it's not written here, it was in the first slide. You can see where this relates. So sigma at 1 cannot be 0, so kind of technical assumption. This 1 was exactly our initial condition. And so this guarantees that actually the standard deviation is larger than 0, so it makes sense to divide it by, we cannot divide with 0. But also, if this would be 1 and your initial condition is 1, there is then nothing to actually to study. Then we get trivial solution. It stays at 1 and that's it. Well, that's easy to analyze. Then what else? So we were only considering a large ball centered at origin, but you can use stationarity to look at other balls centered at somewhere else. Actually, also your center can vary in capital R, so it really doesn't matter where in space your ball is located. If it's large enough, your average temperature is close to Gaussian. And then also, so Y ball, it's easy to present the result for that. Any other body works. You just, let's say that, okay, it doesn't have to be convex or anything. You just take some body, A0, and then you look at the so it scales correctly. So you look at simply this kind of set. So you let this grow to expand to everywhere. You get exactly the same result. It just affects the constants. So for example, here this C, you have actually involved an integral over a ball of radius 1. So then you would have integral over A0 and things like this. Okay? Good. So what else? I also promised the functional version. So this was the third question. Again, looks very technical. But point is that, okay, now we use the difference scaling. This is simply the standard deviation. That's a little bit of that. We look at this as a process, and it converges as a process towards this thing. And here, y is a Brownian motion. So we get a Gaussian distribution in the limit for each fixed t. And as a process, we don't get exactly the Brownian motion as in the classical central limit theorem case. Okay. But something very close. So this is just a deterministic function, so the point is that we get a Gaussian margin. And because it's a Gaussian margin, the limiting object, you get, for example, the independence of the increments for free. So this is kind of, gives again something more. Okay, so what we can do then is that I mentioned that I will also give out those results in the space-time wide case. So this is very similar. You look at the total variation distance, you have constant, and now your rate is classical 1 divided by square root of r. In the previous version, in the color case, you have this parameter beta coming from the real kernel, but then because you don't have that, you get some rate. And also the limiting random process is very similar. So here you have Brownian motion and again a Gaussian motion. But of course this works only in dimension 1, because even the very solution which I gave you in one of the first slides holds true in the space-time white noise case only in one space dimension. Okay, any questions related to results? Because I think this is kind of the stochastic partial differential equation part is over, more or less. I will prove these results, but as I mentioned, I will now explain what you can do in such situations, and then it's very straightforward to apply the general tools to our case. So what is the general idea? Okay, we have stationarity, but assume for a moment that you are looking whether something converges towards a normal distribution, but you don't have independence, you don't have stationarity, you have nothing. You just have some sequence of random variables. So Stein, some time ago already, provided a way to obtain a central limit theorem beyond these classical assumptions, and he proved actually this kind of inequality here. So again, we look at the total variation distance, And what is your upper bound for that is this one. So note that this depends only on your random variable f. So in particular, you plug in your sequence. And then you have some function small f. You have the derivative of it, and then it appears here also. And now you take supremo of this difference over all C1 continuously differentiable functions, such that the function itself is bounded by this and the derivative by 2. So very nice result by Stein. So this is kind of works for any random variable, any sequence. Of course, how to really to compute this kind of supremo over a class of functions. Well, I think it was not applied actually not a lot, especially because of this problem, until recently. People have noticed that this Stein method and Mallian-Baer calculus works very nicely together. And Mallian calculus I will briefly give the elements soon, but it allows basically to differentiate random variables and random processes. And remember, I explained that typical noises, they are, for example, Brownian motion. It's non-differentiable. It's not a bounded variation. It's nothing, but you can, in some sense, compute the derivative of that. And then, with the help of Mallian calculus, we can basically compute this one. Okay, so a couple of slides containing very basic elements on Mallian calculus. Not that important. I will explain what is kind of we are examples how this is useful. So what you always have is that we have our Gaussian object. We have some Gaussian space. So in our case, it's this covariance of the Gaussian noise. And then we simply look at the Hilbert space. If you consider the Brownian motion case, you look at indicator functions, and you look at the actually quite easier to over some interval, and then because Brownian motion has independent increments, you can basically look at this. So for indicators, you simply define an inner product given by the covariance of Brownian motion. And this works for more general Gaussian fields or Gaussian processes. You have your covariance structure. But in the Brownian motion case, it's very simple, because then this Hilbert space is simply the L2 space. It's a space of functions. But what you have, so you take indicators, you have this inner product, and you close. So you take in all the limits, making it a Hilbert space, because then it's complete. And in the space-time white noise case, we have also kind of then L2 in the product, or L2 product space. But a warning, this is kind of in the white noise case, you get nice space of functions, L2 spaces. In general, this is just some abstract Hilbert space. This might not even be a space of functions. It might have distributions in. And then basically, we can simply associate kind of for each element in this space, we have a one-to-one correspondence between Gaussian random variables generated by the same process. It's called the isonormal process. And then we can define the Malliamin derivative. Again, this is, if you're not familiar with the topic, don't worry. This is the formal definition, but basically what we get, we take something simple, we define the derivative, and then we close with respect to some norm. As in mathematics always, we take something that we can understand, its natural definition, then we pass it a limit in some sense, and the difficulty is to say what is the correct sense in your particular case. But maybe the examples are important. So you look at the process. Okay, this is the Brownian motion, but any process works. You take the derivative, it gives you back the indicator. So kind of, I have the process, I differentiate it, it gives me an indicator, which belongs now to this Hilbert space. Similarly, if I look at the process to power 2, I differentiate, it's kind of, okay, derivative of x squared is 2x, so you get 2bt still here, multiplied with the same indicator. So then you have an element which is still random, but then you have also an element belonging to this Hilbert space. And then we also kind of have the adjoint operator, which is, or the divergence operator. It's simply, well, the derivative and integral plays nicely. One goes to other direction, and then another to the other direction. This is the same here. We differentiate this, we get the indicator. You apply this operator to the indicator, you get the process back. So this is kind of an antiderivative. And you can also view this as an infinite dimensional generalization of a classical divergence operator. And also kind of as a stochastic integral. Anyway, to the point. So this is a little bit technical. What you can do is that I proved this one, this Stein. This was the Stein's. And to compute the right-hand side, you get something like this. Now this starts to annoy. Now it's better. So we take, again, we compare to the standard normal, and we take anything that is centered has variance 1, so you just divide with the standard deviation. If this f is now a center, such a random variable, such that it's square integrable, it has some, it's Malliamin differentiable, and the derivative is also square integrable. And also if you can represent it as kind of, in a sense, as a stochastic integral of some b. So this is this adjoint operator. Then what you get, this total variation distance is bounded with this. So you have 2 in front. 2 is coming exactly here, on the bound of the derivative. And then what is inside? So you have square root or standard deviation of 1 random variable. And why this is very useful is that, okay, you can think basically as your model already. You can consider that your sequence lives in some Gaussian space. It simply means that there is some underlying Gaussian structure where all the randomness comes. It can have any distribution, any dependent structure. So I want to emphasize that you can have a lot of things there. Basically, well, anything that is square integrable. It does not mean that you have Gaussian objects that are normally distributed. It simply means that kind of you think of that there is some Gaussian thing that gives you all your randomness. If this is the case, then basically the space for which you can compute the Malliamin derivative is very large, and you can actually compute it. It might be complicated, but you can compute it. And also, you can find this representation. So what is left? You have two objects, you have your derivative, you have your b, you can compute them, and then you have your Hilbert space, which you know also exactly what is the inner product. And then you compute the inner product, you have some random variable. And then you compute its standard deviation. So this is, you have one random variable. It might be complicated, but you can explicitly compute it, and you simply compute its standard deviation. If that converges to 0, you get the limiting normality immediately. No stationarity, no independence, nothing assumed here. Only that you really need to have a random variable for which you can compute this Magliari derivative. So what, I have 6 minutes left. In our case, this was the object we were studying. And if we write it, I write the solution again. It's exactly this one. So here you have -1, this one goes to the other direction, and then you integrate, so you apply Fubini theorem, you get the integral inside, you come up to this representation. And this is exactly gives your b immediately. B is just the thing here inside for which you are integrating. Well, then the derivative is linear operator. You compute it from here. On the other hand, starting from here, you can again, it would be very easy to check if you assume everything can be done formally. So you just differentiate here. So this vanishes, and then you use the product rule here. You come up to this formula. And now you have kind of sigma u here, and here you have again the derivative of the solution. Well, looks something very familiar from the theory of partial differential equations also, so we can apply some kind of Grönwald type argument to actually look at what is exactly the norm of this derivative operator. And we get some universal constant and then the heat current. As a result, we compute this one here. So you get, if I remember correctly, 16 iterated integrals, but it's just the products of heat kernels. So you integrate them one by one, use the semi-property, and in the end you are simply integral from minus r to r in the one-dimensional case, or over one more. And then it's kind of, we get the result easily. You need to apply some technical computations a lot, but it's doable, and this is kind of very useful here. Okay, the functional convergence, for that you need two things. One is the convergence of finite dimensional distributions. This you can do exactly as the proof of total variation distance. You just again use some multi-dimensional version. And then you need the tightness, which is kind of that if you have convergence of the finite dimensional distributions, the tightness kind of squeezes the whole process to follow kind of the same thing. And for that, it's sufficient to simply look at some moments of the increments. And this is again something that you can really do. Okay, maybe I have 1 minute left. So some future questions. First of all, why heat equation? So the same questions have been asked in the case of wave equation. So David Molarco, my co-authors here, with his student, worked out the details in the case of wave equation after we did this. And now we are working on the case of fractional Laplacian, so kind of fractional version. So you replace Laplacian with the fractional Laplace operator. And in the wave and heat equation case, we get this fundamental bound here. The same seems to happen in the case of fractional Laplacian, so kind of it's bounded by the fundamental solution. Fundamental solution was the solution without the random one. To what extent this is universal property? Because this is then, you can easily, this is somehow universal. You can basically work out the whole machinery goes through for more general SPDs, stochastic partial differential equations. Then, of course, now we consider the whole space, but maybe this is not physically meaningful. You have only some large body and you have some boundary conditions. What if, okay, I cannot let my R to go to infinity if I have the boundary, but if I have a large body, I could kind of consider how far this is with these boundary conditions, the solution is with the boundary conditions if I compare this, to the equation in the whole R. If these are close and the object in the whole R is close to a normal, then maybe I can do something. And then other SD and SPD problems also I'm working on with several co-authors, especially with Ingrid Torres and Paulina Ilman, who are here in the audience. Thanks. One second left.
Questions? Comments?
In your result about the total variation theorems, can you obtain a similar result if you change Gaussian distribution by a sub-Gaussian distribution?
I think there are some, okay, point is that if you have the Gaussian distribution, then everything comes from actually the integration by parts characterization of the Gaussian random variable. And I know that there are some works on Stein's method in the sub-Gaussian case, and also kind of, you can change the limiting your target distribution, but then you end up to different equation, and it's kind of, you cannot, I'm not sure whether you can directly apply the same one, but you can obtain some bounds, and this is actually a topic of active research, because you can consider some non-Gaussian limiting things and how to get these studies to work.
More questions?
Can you mention the effects of boundary conditions?
Yes.
Because you are working in a world, but what happens if you are completely outside of the world? I mean, the boundary domain is not so regular as
Well, you mean this future question?
Yes.
So I have my boundary and
yeah.
so yeah, as I mentioned, so this result holds easily for any domain, but the boundary conditions on different domains, that has a huge effect, and this is a natural question, but I cannot answer directly. I would guess that it really depends on your boundary conditions. Because this result works if you just expand, but now, depending on your domain, the boundary conditions have different effect, and I cannot say directly how far then your solution is if you compare to the one without the boundary conditions.
And concerning, I think it's more or less the same question, concerning how go far from the Gaussian case. For a statistical point of view, you need the force want to have a limit distribution or a static distribution.
So the fourth moment actually is encoded in what I wrote.
But what happens if you are a little bit far from the Gaussian noise? For example, the suppression or the Poisson noise. There is some equivalent to the Gaussian phase.
So you mean that your objects are living in the Poisson space?
For example.
But there is a fourth moment. There are versions of fourth moment in the Poisson space also, and also in the Wigner phase. Because so we consider random matrices. This is kind of. So there are things by and well, I suggest to look the papers by Giovanni Peccato on this because he worked on this.
Comments? One more?